To help speed along our ability to evaluate logarithmic expressions, it can be useful to keep in mind a few key concepts, key ideas. And again, this all relates back to rewriting logarithms as exponentials to understand why some of these properties are what they are. So for example, if we take the log of 1, and again, it does not matter what the base is. It could be base 10, could be base e, could be base 2 or 3, like we saw in one of our other examples. So the log of any base of 1 is always going to equal 0. And the reason for that is, if I rewrite it in exponential form, my base of the logarithm becomes the base of my exponential, so a is the base, and then the 0 is the exponent, because a logarithm is an exponent. So a to the 0, well, it doesn't matter what a is. If I raise anything to the 0 power, I get 1. So therefore, it doesn't matter what the base is, log any base of 1 is always going to equal 0. So that's one property that can be useful. A second is if the base of the logarithm and what you're inputting into the logarithm match. So log base a of a, log base 2 of 2, log base 3 of 3, log base 10 of 10. Natural log, remember that's base e, natural log of e always equals 1. And again, if I rewrite this in exponential format, we can clearly see why that's the case. The base of my logarithm becomes the base of my exponential. A logarithm is an exponent, so the output of my logarithm becomes the exponent. Well, if I raise a number to the first power, I always get that exact same number. So therefore, a to the first equals a, so that means log base a of a equals 1. And then the third property that we have here is that we can never take the log of 0, and we can never take the log of a negative number. And again, if we rewrite this in exponential form, we can very quickly see why that's the case. So let's say we had just something over here like x. So if we said log base a of 0 or a negative is supposed to equal x, well, that would mean a to the x power would have to somehow equal 0 or somehow equal a negative number. Well, of course, we know when we take a number a and raise it to an exponent, we're always assuming a is positive, which by definition for exponential and logarithmic functions it needs to be. We're only going to get positive results. So if we think of what an exponential function looks like, it has a horizontal asymptote along the x-axis. So our outputs are always going to be positive. We can never hit 0, we can never go negative. So if our output of an exponential function is never going to be 0 or negative, then that corresponds to the input of a logarithm. So for that reason, there's no number that we can plug into a logarithm or into an exponent here to make 0 or a negative, so therefore we can never take the log of 0, we can never take the log of a negative number. So if we jump down to the examples that we see below, so start with the first one here, log of 10. Well, remember, if there's no base listed, then that implies that it is base 10, the common logarithm. Well, if the base of the log and the number we're taking the log of match, then right here, that means our answer is going to equal 1. For the second example, log base 2 of 1. Well, again, any log base of 1 always equals 0. So our answer here is 0. It didn't matter that it was log base 2. What mattered is that the input into the logarithm was 1. For the third example, we're back to the idea of the base of the log and the number being input into the log matching. When that's the case, our answer is automatically 1. ln of e. We don't want to read that as ln. Remember, that means natural log or log base e if we want to see it written that way. So this is another example of where the base of the logarithm and the number inside the logarithm match. So therefore our answer here is 1. For the next example, log of 0. Yes, it's base 10, but that doesn't matter to this question. We know from right up here that we can never take the log of 0. We can never take the log of a negative number. So our answer is undefined in this case. There's no solution possible. And then for the last one, ln means natural log, or that same log base e, but that really doesn't matter because any log base, if we input 1 into the logarithm, if we try to take the log of 1, our answer is always 0. Now for some logarithmic equations, we can solve by rewriting them as exponentials. Again, that's the common thread everywhere here, is we don't have a lot of familiarity with logarithms, so let's rewrite them as exponentials. Now in the case of these equations here, we have to isolate x, and so when x is inside of a logarithm, the way we're going to isolate it is by rewriting it as an exponential. Just like we'll see in the future, if we have an x in the exponent and we need to get it out, the way that we can do that is to rewrite it as a logarithm. But here, we're going to take these logarithmic equations and rewrite them as exponentials. But before we can do that on the first one, we have to isolate the logarithm. So we can't rewrite it until the log is by itself on one side of the equation. So I'm going to take both sides and divide it by 2. So now I've got log base 4 of x equals 1/2. Now I have the logarithm isolated. I can rewrite this in exponential form. So the base of my log becomes the base of my exponential. A logarithm is an exponent, so 4 to the 1/2 equals x. Well, hopefully we recognize a 1/2 exponent is really just meaning a square root. So really this means it's the square root of 4, so our answer is just 2. Not plus or minus 2, just 2. We're just taking the square root of 4. In the second example, do the same thing. This time the logarithm is already isolated, so we can go ahead and rewrite it right away into exponential form. Base of my log becomes the base of my exponential. What my logarithm equals is an exponent, so that's going to put the 2 here, equals the input into the logarithm 6x. So just following the pattern from the very start of the notes. So now 9 squared, don't say 18, that's 81, equals 6x. So my last step is to just divide both sides by 6. And we can just leave our answer in fraction form. We can reduce that fraction, divide the top and bottom by 3. So we're going to get 27 over 2. For our third example, again, the same approach. Base of my log is the base of my exponential. The output of the logarithm, so the answer to the logarithm, is the exponent, so 3/2 equals the input to the logarithm x. So raising 27 to the 3/2, again we're using our exponent rules here, so the numerator is the power on the variable or the input, and then the denominator is going to be the root, so we're taking the square root of 27 to the 3rd power. That's going to equal x. So there's a number of ways I can approach this, but one way would be to write this out as 27 times 27 times 27 underneath that square root symbol, and then I can see I have a pair of 27s, so that's going to come out as a 27. Then I've got just the square root of 27 that's left. Well, that breaks down into 9 times 3, so I can take the square root of 9, so that comes out as a 3, and then I still have a 3 trapped underneath the square root symbol. So if I eventually clean that up, 27 times 3 gives me 81 times the square root of 3 is the answer to this equation. And then for the last one, in this case, it's a little bit different than all the others because instead of it being a logarithm on one side and just a number on the other, this time we have a logarithm. Log base 3 of x plus 3 is equal to log base 3 of x squared minus 9. And so in this case, we don't need to rewrite it as an exponential. Instead, we can go ahead and recognize that for this equation to work, if I'm taking the log base 3 of something over here, and I'm taking the log base 3 of something else over here on the other side, well, these two things inside of the logarithms have to be equal to each other. Or in other words, x plus 3 needs to equal x squared minus 9 for this problem to work. So here I have an equation that's a quadratic equation, so I'm going to solve by setting it equal to 0 and checking to see if I can factor or use some other technique. So if we do that, I'll move everything to the right, so I'm going to get 0 equals x squared. I'll subtract x from both sides, so I get a minus x, and if I subtract 3 to both sides, I get minus 12. So clearly this is a factorable expression, so that's the approach I'm going to take here. So I need a positive and a negative since I'm multiplying to make negative 12. I need to add to make a negative 1 in the middle, so my factor pair is going to be 4 and 3. So I'm going to have minus 4 and plus 3 to make this problem work. So if I set each of these factors equal to 0, I get x plus 3 equals 0 and x minus 4 equals 0. So my two answers that I'm going to get out of this quadratic equation are negative 3 and positive 4. But because this is based off of a logarithmic equation, we need to make sure that both of those answers work. And if you'll recall, we can't take the log of 0, we can't take the log of a negative number. Well, negative 3 is going to be a problem, because if I plug negative 3 in for x into both of these equations, or sides of the equation, we're going to get 0 as the inside of the logarithm. Log base 3 of 0 doesn't work, so I need to throw this answer out. If I plug in 4, however, on the left side, log base 3 of 4 plus 3 is 7, and then on the other side I'll get the same thing. 4 squared is 16 minus 9 is 7, so I'm getting log base 3 of 7 on both sides, so that works. So my only answer in this last example is x equals 4 after I throw away the extraneous solution.